Hello everyone. I welcome you to another session of IR spectroscopy. This is Sarita Rani, Assistant Professor of Chemistry, Government Degree College for Women, Begumpet. So we have completed two parts of IR spectroscopy. In these two parts, we have completed the principle involved in IR spectroscopy, different types of molecular vibrations, and how to calculate the number of vibrational modes for linear and non-linear molecules. And we have also seen the factors affecting the vibrational frequencies and the instrumentation part, that is FTIR, Fourier transform infrared spectroscopy. Now, in that we have seen that the time domain spectrum has to be converted to frequency domain spectrum. So how it was converted, that is a complex spectra has been converted into a frequency domain spectrum so that it is very easy for us to analyze the spectra. So now in today's class, we will discuss about the applications of IR. So what are the applications of IR? As we all know that IR spectroscopy is very useful for the determination of functional group present in the given sample. So now we'll look at what are the characteristic vibrational frequencies of various functional groups. So the applications of IR are, the main application is to identification of an organic compound. That is to measure the spectrums, because we know that no two samples will have the identical IR spectrum. So each and every individual functional group or a sample of organic compound will have different IR spectrum. So with that, we can easily find out what is the exact molecule. So these are the structural or the functional components. So here we can see that is on the x-axis, we have the wave numbers, and on the y-axis, it is percent transmittance. Now, the range of IR, we know that it is from 4000 to, we actually take it as 400 centimeter inverse. So 4000 to 400 centimeter inverse range of the sample, or that is of the IR spectra, IR region, is very useful for the identification of the functional group. So in this case, here you can see from 3500 to nearly about that is 3000 mark, and this is 3500. So all these functional groups, stretching vibrations, we can observe in this region, NH, OH, CH. Whereas C triple bond C, C triple bond N are observed in this region from 2000 to 2500. Then C double bond C, C double bond O, C double bond N, that we observe between 1600 to 1800. And the region which is below 1400. So below 1400, this region we call it as a fingerprint region. Whereas the region from 4000 to 1400, or sometimes in some books it will be written as 1500. So that area is considered as the functional group region, because the that is the peaks whatever we get, or the bands whatever we observe between 4000 to 1500 centimeter inverse are because of the functional group vibrations. Whereas below 1500, it is fingerprint region. Mostly they are bending vibrations. So in this you can see that 4000 to 1400, it is a functional group region. So from till here, then the fingerprint region from 1400 to 600. And all these are low energetic. The fingerprint region falls under low energetic, whereas the functional group region is a high energetic. So by all the study of these spectra, the absorption peaks where it is observed, we can easily identify the functional group which is present in the sample. So this is the fingerprint region again. So here it is at greater than 1500 is functional group, and the fingerprint region is at below 1500 centimeter inverse. Now this is IR correlation diagram. So we have to first learn the stretching vibrations at which region they are observed. So generally here we can just simplify this in this way. Region 1, region 2, we have written here. So it is 3600 to 2700 centimeter inverse. So what are the functional groups stretching vibrations that we observe in this region are alcohols, phenols, carboxylic acids, then NH stretching, that is we observe OH, NH, CH bond stretchings. So all these functional groups come under that. Amines, amides, then alkynes, alkenes, alkanes are also observed. So here we are taking from 2700 to 3600 centimeter inverse. So this range you have to remember. Mainly it is the peaks observed are for OH, NH and CH bond stretchings. Then in region 2, the region 2, it is 1800 to 1600 centimeter inverse. So main functional group what we observe here is C double bond O, that is carbonyl functional group. So carbonyl functional group means what are the functional groups that has C double bond O group? They are acid chlorides, anhydrides, esters, ketones, aldehydes, carboxylic acids and amides. So all these functional groups, they lie in this 1800 to 1600. That means in all these functional groups, we have C double bond O group. So C double bond O group stretching vibrations, they are seen in this region. Then below this, actually it is a fingerprint region. So these are the main values we have to remember. And here you can see it is triple bond CH, double bond CH stretchings and single bond CH. That is sp3 carbon, this is sp2 and this is sp carbon. This is sp, sp2, sp3. So these CH stretching vibrations are observed in this area. Now we'll see one by one each functional group frequencies. So first, the use of IR is, as I said, it is used in the identification of functional groups of the molecule. And it is also observed, we can also study this for quantitative analysis. So quantitative analysis according to the Beat's law, that we'll see later. So how it is also used for quantitative analysis of the sample. Then the features of IR spectrum. So as we have seen in the last class itself, the spectrum is nothing but the plot of percent transmittance against the wave number. And 100% transmittance means it won't give any absorption band. But when the transmittance is there, then only we can see the dip in the absorption band. So you can see when a compound absorbs IR radiation, the intensity of transmitted radiation decreases. So when the absorption is more, as we know that absorption and transmissions are inversely proportional. So when a compound absorbs high percent of radiations, then the transmittance will be less. So that is the reason the peak goes down. That is, there will be a dip in the spectrum. So that dip is called as absorption peak or the absorption band. And these absorption bands are different for each and every bonds, that is CH, OH, NH, etc. So all these we'll see. Now here you can look at the spectrum, IR spectrum, general IR spectrum we are showing. So this is the baseline. So baseline is this one. So that means here what is the meaning of this is, here there is 100% transmittance or just near to 100%. So as we are moving like this, so suddenly there will be absorption of the radiation. So that is why when absorption is more, what is happening to the transmittance? It decreases. Okay, it decreases around 15 like that, 15%. So the transmittance is decreasing. So that is why it is showing, it is moving down, and then again the transmittance will be high. So in this way, these peaks, or we call them as absorption bands, because due to this absorption only, this band is appearing. That means after absorption, the transmission will be less. So that is why here, as on the y-axis, we have taken transmittance. Transmittance will decrease because absorption is more. So these are the absorption bands. Now, in this absorption bands, we have some bands as very strong, that is they go till down of the, that is almost they will touch the x-axis. So they are known as very strong, and some are less than that, that is strong. Some will be medium, weak bands, broad bands, and sharp or shoulder bands. So this is the notation we use. VS means very strong, S is for strong band, M is for medium, W is for weak, BR is for broad, SH is sharp or shoulder. So in general, so these are the IR spectral regions that we have splitted them into 4 regions here. So just for our convenience, so that we can remember the vibrational frequencies of each and individual functional groups. So you can see from 4000 to 2500. So as we have seen the first slide itself. So what are the groups we have to remember? That means it may contains OH, NH and CH stretching vibrations. Then 2500 to 2000. That means C triple bond C, C triple bond N. Then 2000 to 1500. It is C double bond C or C double bond O. Then 1500 to 400. This is nothing but a fingerprint region. So it is rarely used for the identification of particular functional groups. That means when the two compounds are having almost near structure, only they are differing in the position of the bonds, then position of the groups, then we can go for this fingerprint region to identify what are those two different molecules or the samples which are present. So the same thing, we are representing it on the spectra here. So NH, OH, CH stretching vibrations from 4000 to 3500, or that is 3000. C triple bond C, C triple bond N from 2000 to 2500, and C double bond C, C double bond O, C double bond N 1800 to 1600. And in the fingerprint region, we come across all these CC, CO, and CN. Now, these are the minimum base values we have to learn. So, without knowing the frequencies, we cannot interpret a IR spectra. So, OH, this is the values which are given plus or minus 10 centimeter inverse, because the same exact value no one can remember. So it may be it may be either addition of 10 or subtraction of minus 10 will be there in any of these readings. So first highest is for OH, because we have hydrogen bondings there. So 3600, then comes NH 3400, CH 3000. So same thing, C triple bond N, C triple bond C around this 2200 mark, you remember like that. Then C double bond O will be 1715 or almost near to 1750 like that. C double bond C is 1600s. C double bond O is around 1100. So these at least 100 difference it may be, but you can remember as we practice the values again and again, we can easily memorize them. Now let us see OH stretching. So OH stretching, where do we find? In this region. So OH stretching region 3600 centimeter inverse for alcohol which is free. So alcohol functional group has OH. So that alcohol group, whether it is present or not, that we can identify by this absorption band. Around 3600, if we find a sharp band, that means it is due to OH group. And that too, it is a free OH group without any hydrogen bonding. Suppose if hydrogen bonding is present, what is happening? The vibrational frequency is decreasing. So we have seen in the last class also, the vibrational frequency affects or it decreases because of the hydrogen bonding. So what happens when hydrogen bonding is present? The force constant will decrease. That is between oxygen and hydrogen, the bond will get, the bond length increases. So therefore, the bond strength decreases. So when bond strength decreases, automatically vibrational frequency also decreases, because vibrational frequency is directly proportional to the force constant. So in alcohols and acids, we come across a decrease in the vibrational frequency around 3300, which is broadband also. Okay, broadband because of the hydrogen bonding. Now the same thing what I said. So this is all, you can see the hydrogen bondings between the alcohols. So when a hydrogen bond is formed, longer bonds are formed, they are weak, and therefore the absorption is decreasing. Then free hydroxyl group will have higher bondings. So you can see free hydroxyl group where we have taken this in a dilute solution of alcohol. This is in an inert solvent like carbon tetrachloride. So there are no hydrogen bondings formed here. So that is the reason only the ROH, that is alcohol, is surrounded by these solvent molecules, and there won't be any probability of formation of hydrogen bonds. So that is the reason why the vibrational frequency of OH will be more for free alcohol groups. So with an example, we can show the spectrum. It is cyclohexanol. So this is cyclohexane ring, to that OH group is attached. So cyclohexanol, you can see OH group is present. So we should find an OH stretching vibrations, where we should it should appear from 3300 to 3600. So here you can see a broad band, a little bit broad because of hydrogen bonding. Actually, it should appear at 3600, and that too it should be sharp. But because it is a little bit broad, and it is appearing at 3300 like that, we can say that there is a hydrogen bond formation which has been taking place here. And all the other bands, you can see this is of CH, and this is CH2 stretching, CO stretchings, because here we have carbon and oxygen. So CO stretching will be less, around 1100. So here it is 1070, medium band. Now here, one thing we have to remember is the base value. What we have to first to look at is the 3000 mark here. At 3000 centimeter inverse, if we have a band just below 3000, so here as we can see 2935 and 2858. So these bands are due to sp3ch stretching vibrations. It is two bands appear because of asymmetric and symmetric sp3ch stretching vibrations. So always first, whenever a spectra is given, just find out the bands which are appearing around 3000. So just below 3000 means it is sp3ch. If it is just above 3000, it will be sp2ch stretching. Okay, just above, that means might be 3100 like that. And if it is 3200, 3300 like that, it might be spch, that is triple bond carbon hydrogen stretching vibrations. So that we'll see anyway. So for now, you just remember that just below 3000, it is alkane, that is sp3ch vibrations. Then another example where we can find OH bond is butanoic acid, that is a carboxylic acids. So you can see OH bond, okay, it is appearing at, this is about 3000, that is at around 3200 it is, and it is very broad. Okay, when you compare with the last one, this is very broad. So why this is broad? In butanoic acid, in acids, carboxylic acids, more hydrogen bondings will be there. That is when it is present in the form of a dimer. So because of the dimers which are present, hydrogen bondings, we will see the hydrogen bondings, and then the spectra or the band is very broad. And because it is also having C double bond O, this is also important. C double bond O stretching vibrations, they are seen at 1714. Okay, So remember now, 1700s means C double bond O. And OH is at 3300 to 3600. And a band just below 3000 again. What is that? It is sp3ch. Okay. So like that, 2, 3, 4 bands in each and every spectra. If we remember the values, you can just memorize them and it will be very easy for you also to learn. Okay, C double bond O around 1700, you remember like that. So this is the spectra of butanoic acid. So as I said, carboxylic acid, it exists as a dimer. So because of the strong hydrogen bonds in the dimer, which weakens the OH bond, and it leads to a broad peak at the lower frequency. So that is the reason. So whether it is a alcohol or carboxylic acid, if we want to differentiate, the one very thing we have to remember is OH, that is in alcohol, OH will be a little bit broad, whereas in carboxylic acid, it will be broad, as well as the another peak what we have to observe for carboxylic acid is C double bond O. Remember that, because the C double bond O band should also appear for carboxylic acid. Then only we can say that it might be a carboxylic acid functional group. Now NH stretching. So we have completed OH group, then we are going into NH. So NH also falls in the same category, same region. Now NH means we find this in amines. So amines we have 3 different types, that is primary amine, secondary and tertiary. Now here we are showing primary amine, which is NH2. Okay, so 2 hydrogens which are attached to the nitrogen. Now here again we can find the stretching vibrations, two types of stretching vibrations. Those are symmetric and asymmetric stretching vibrations. So you can see this is symmetric, both hydrogens moving away, whereas here this is asymmetric, one hydrogen is moving towards the nitrogen, whereas the other hydrogen is moving away from the hydrogen. So because of this symmetric and asymmetric, 2 bands or 2 peaks appear for primary amines. This is very important point you have to remember, because IR can distinguish primary, secondary and tertiary amines. Okay, so how we can distinguish is primary amines will give 2 bands. In which region you have to see? From 3300 to 3400. So in that region, if there are 2 bands, it might be due to primary amine. Whereas for secondary amine, we will find only 1 band or 1 peak. Because why only 1 peak? Because only 1 hydrogen will be there for secondary amine. What is secondary amine? Here we will have an alkyl group R, N, another atom or group will be R, and 1 H will be there, which is attached to nitrogen. So that is the reason secondary amines will show only 1 peak, whereas tertiary amines will not at all show any peak in that region. Okay, why it will not show? Because in tertiary amine, nitrogen is attached to 3 alkyl groups. Okay, we don't have hydrogens which is attached to nitrogen in tertiary amine. So because there is no hydrogen, there won't be any NH stretching vibrations. Okay, so primary amines will show 2 bands, secondary amines shows 1 band, tertiary amines show no bands. Okay, now we'll take an example of primary amine first, that is 1-butanamine. Now 1-butanamine is primary amine. So NH2, this is the structure, NH2, nitrogen having 2 hydrogens. So 2 bands. So these are the 2 peaks. Okay, so 2 peaks appear. And what is the range? From 33 to 34. So almost just around 33 only this is. So this is how we have to distinguish. Okay, it might be due to NH2. And again you can see that is below 3000. Again bands, 2 bands. Okay, that is again, what does it say? It is due to CH stretching, sp3CH. Okay, that means the given carbon group is sp3 carbon. And when we are having NH2 groups, we have to look for NH2 scissoring. That is the bending vibrations. So bending vibrations they appear at 1600s. So 1601 here. Then these are CH2, CH3 bending vibrations. So all these are very, that is general thing what we have to look for is till from 4000 to 2000 or near 1500. From 1500 to 4000, the bands whatever appear, that will give a lot of information for us. Okay, less than 1500, it is very difficult to actually interpret. But first thing is we have to interpret these bands because they will give the information about the functional groups. Then another example of primary amine only. So why we have taken another example is, see again it is primary amine. So these are the two bands for NH2 stretching. And why we have taken is, here you can see just above 3000. That means it is 3036. So this is due to AR. AR stands for aryl group here. That is aromatic ring. This carbon is what? It is sp2 hybridized. Okay. So sp2 carbon hydrogen. Whereas the peak above will be sp3 carbon. Peak below 3000 will be of sp3. So here in this spectra, you can find above 3000 one band and also just below 3000 another band. So what does we can, it is giving information that this might be due to sp2ch stretching vibrations and this might be due to sp3ch stretching vibrations. So this is how, because there is a CH3 group, so we have one sp3 carbon which is having hydrogens. Okay, and all these around 1600 also if we have to find, we have to look for 1600 because another point what you have to remember is in aromatic systems, C double bond C stretching vibrations will appear around 1500 to 1600. So all these bands, these two bands might be due to C double bond C stretching vibrations. And not only that, when we are having substitutions on the aromatic ring, okay, so when substitutions are present on the aromatic ring, we should find the bands below 1000. So below 1000 or 900, we have to look for the bands. All these are bending vibrations of sp2ch. Okay, aryl means it is sp2 carbon here, sp2ch bending vibrations. So because of this below 900, we have to look for the number of bands. Those number of bands will give information about the substitutions which are present on the aromatic ring. Okay, here you can see it is ortho meta. So it is meta substituted or 1, 2, 3. It is 1,3 disubstituted benzene. Okay, so for 1,3 disubstitution, we find two bands below 1000. So in that way, we can interpret that these two functional group NH2 and methyl group are meta to each other. So that will again see. So just remember for this structure, these are the main bands what we have to look for. That is, one is functional group, that is NH2. Okay, then the other is when it is having aromatic, compulsory there should be a band just above 3000. Okay, and also we have to look for this skeletal bands, C double bond C stretching vibrations. Okay, and then if it is disubstitution, bands below 9000. Okay, these three regions you have to remember for aromatic regions, aromatic compounds. Now this is secondary amine. It is N-ethyl benzenamine. Here you can see again there is only one band, right, at 3403. So this one band indicates that it is a secondary amine. And one more thing, just know what I said, it is an aromatic. Okay, just above 3000 we have to find. These are the peaks actually, but it is not clear in this. And these are the groups, C double bond C stretching vibrations, 1600, 1510. Okay, and again you can see there are below 900 also there are bands. Now NN-dimethyl-aniline, it is a tertiary amine. It is not having any hydrogen which is attached to nitrogen. That means there is no NH stretching vibrations. This we have to remember. So no NH stretching vibrations because it is a tertiary amine. So what we will have? We have only sp2ch. This one 3031 refers to sp2ch stretching, and this is sp3ch because we are having methyl groups. And this is again benzene, C double bond C stretching vibrations, and then below 900 also we have. So that means it is giving information about that it is an aromatic ring and it is a tertiary amine. Tertiary amine, how is that we are saying it is tertiary amine? Because there is no band between 3300 to 3400. Okay, so in this way we can distinguish primary, secondary and tertiary amines. Now next is CH stretching. So CH stretching is again the same region. So CHSP, that's what I have told you. CHSP is 3300. SP2CH is just greater than 3000. And SP3CH is just less than 3000. So that is the reason you have to make this point where 3000. So at the 3000 mark, we have to look for the bands very carefully. So base value at 3000, you have to remember. And then CH aldehyde. Then this is also another important point, whether a compound is having aldehyde or not. We can look for these two peaks which are weak, that is 2850 and 2750. So at 2850, 2750 compulsory we have to observe for aldehyde functional group. So stronger bonds have larger force constant and absorb at higher frequencies. That we have seen in the last class itself. That is the factors affecting that is vibrational frequencies. So triple bond SPCH, it is because 3 bonds, large amount of energy is required. So that is why force constant will be more. That is K value is more. So vibrational frequency will also be more. Then comes CH, this is sp2ch, which is less, 3100. Then just below 3000, it is sp3ch. And then as I said, aldehyde 2850, 2750. So 2 peaks for aldehyde. So we are taking an example of alkane now. So alkane, it is having all carbons are sp3. So where we have to observe the peaks, as I said, just below, because for alkanes it is just below. Just 3000 above is for alkenes, and if you go further around 3200, it will be alkynes, that is sp carbon. So 3000 mark, just below that, it is sp3 carbon. Okay, by this we can say that it is a alkane group, that is alkyl group. All the carbons are sp3 carbons, and these are CH bending vibrations. So CH bending, we this just remember that 1300 to 1400, okay, 1300 to or 1450 CH bending vibrations are observed. So all these, why we observe these CH bending are because of scissoring, wagging, rocking, twisting. So 1465, 1250, 1250 here, 720. So all these are bending. So bending vibrations does that is after finding out the functional group only, then we have to look for the bending vibrations. So all these are same. Okay, now this one, methylene and methyl bending vibrations. So whether the molecule is having methylene group, CH2 group, or whether it is showing methyl group, that is CH3. So that we can check out by, see here, this is one CH3 which is attached to carbon. So it will show only one band. Actually CH2 will appear at 1465 and CH3 because it will show a symmetric and asymmetric. So 2 bands, 1460 and 1375. Now for isopropyl groups, this is isopropyl group like this. So 2 bands appear for this. Okay, in this region 1380, 1370. If it is tertiary butyl group, this one, for this also 2 bands appear. Okay, so these are the bending vibrations. So the same example again we are looking for is hexane. So now we know that it is sp3 carbon which is present. Now this is CH2 bending. These are because of CH3 bending. And this is CH2 rocking. It is very weak. Now 1-hexene. It is alkene. Now alkane we have seen just below 3000 sp3ch stretching vibrations appear. Now for alkene it is just above 3000. So here you can see 3082 sp2ch stretching vibrations, right? Then we also observe these because of in here you can see there are some other carbons which are sp3 hybridized. So that is the reason we observe even these bands. So these are what? sp3ch. Then C double bond C. This is another important. So we have seen even in the aromatic system, C double bond C stretching vibrations from 1500, 1600 like that you remember. So here also we can see this band is due to C double bond C. Then this 1400s, 1300s all are nothing but bending vibrations. Then toluene, same thing again. So just above 3000. This is CH3 group. Then C double bond CC 1497 1606. So this gives information about the benzene ring. So when we are saying it is a benzene ring, you have to look for the bands below 900, right? So here you can see bands below 900, which are medium bands, medium to strong bands. So that gives information that it is an aromatic compound. In the previous case, you see, this is simple hexene. There are no bands below 900. Okay, so that means it is not an aromatic system. If it is an aromatic system, so we have to look for, first thing is just above 3000, then C double bond C, and then below 900 mark. So these 3 regions you have to look for whether to confirm that the compound is aromatic or not. Then 1-hexene. So triple bond, this is C triple bond C around 3300 as I said. So you can see strong bond at 3300 is C triple bond C, and the remaining is again sp3 carbons only. Then these are again bending vibrations. So fingerprint region. So fingerprint region is very useful to identify or differentiate when 2 molecules are similar but they are not identical. So you can see almost similar, the same frequencies we are observing the functional group bands, but there will be a difference only in the fingerprint region. Okay, so by this we can easily find out what is exact that is bondings which are present in the sample. Then C triple bond and C triple bond C. So we have covered OH stretching vibrations, NH stretching vibrations, and CH stretching vibrations. So in that CH we have seen sp3CH, sp2CH, and spCH. Now next group is CN and C triple bond C. So where they appear from 2000 to 2500. So this region we have to cover now. So we'll do it now. So here you have to remember this frequency around 2200 is for cyno, and less than that will be C double bond C. Okay, so a cyno group will give a strong band or strong or sharp peak due to its large dipole moment. Okay, because of large dipole moment in the cyno group, a sharp band is observed. Whereas C triple bond C will appear weak and it will be less than the cyno group. So in the example, you can see propane nitrile it is. Okay, propane nitrile. See, actually there should be a double bond, one more bond here. So cyno group at 2200, very sharp band. So whenever this appears, it might be due to cyno group. And again, these are same sp3ch just below 3000. Then this is 1464, 1433, these all are bending vibrations. Then 1 hexane. So again, there's a bond missing here. So CH 3308. This is C triple bond CH, this one. Okay, SP carbon H vibration is 3308. And these are again sp3 carbon CH. This is C double bond C, just below 2200. Okay, so it is weak. Then these are all bending vibrations. Then C double bond O stretching vibrations. Now this is very important. So now what we'll do is we'll take this part from C double bond O. In our next class we'll discuss about this. Okay, so till now we have seen the various stretching vibrational frequencies of, that is OH, that is alcohol and carboxylic acid, NH, that is for amines, primary, secondary and tertiary amines, how to distinguish them, and then CH, that is alkanes, alkenes and alkynes. So what are the bands, at what regions we have to look for those bands. Okay, so just revise the topic once again so that you will understand the bands better. Okay, so we'll continue with C double bond O in our next class. Thank you for watching.